All right, what's up, VL AP Statistics students? This is your video for week 6, day 1. We're moving into unit 8 today, and the topic is chi-square tests. All right, so a couple things we're going to do today. I'm going to run through the AP exam and then and the upcoming schedule. We'll do the last couple rows of the inference for means review grid. We have a question of the day, and then I'll get into our work with chi-square tests. Okay, so remember, if you're doing the in-person AP exam, it is fast approaching Tuesday, May 25th. You will report to the library at 11:30. You can use a graphing calculator, bring some pencils with you. If you're doing the digital exam, I'll have more information for you in future videos, but that is Thursday, June 10th after graduation. And you will need to be able to do that on a computer. You can't do it on an iPad. All right, so we're in week 6 here. So again, we're talking about chi-square tests today. And then we'll have a couple weeks of AP review prior to the exam. Okay, so the inferences for means review grid. I have this filled out for you already, so if you want to add this into your document. So remember, in the last video I talked about the paired t-test or and the paired t-interval. Sometimes it's called matched pairs. I'll just run through a couple of these things quick. So the purpose of a matched pairs t-test is to test a hypothesized mean difference between two paired quantitative variables. So remember, when we were doing just the regular two-sample t-test, we were looking at the difference between two means. In a matched pairs t-test, you're looking at the mean difference. So you actually do the difference first, and then you think about the mean. Conditions, we had paired data came from a random sample or randomized experiment. Sample differences are less than 10% of the population. And n sub d, remember that is the number of differences, is greater than or equal to 30, or the box plot of the differences shows no heavy skew or outliers. So remember, with these paired procedures, you always calculate those differences first. So I usually get a big list going of differences in my calculator, and then you're calculating x bar sub d, the mean of the differences, and the standard deviation of the differences. So that kind of leads us into that test statistic. So we do take x bar sub d, subtract mu sub d, that's usually 0, and then divide by s sub d over the square root of n sub d. So again, those are all the statistics that come from that difference list. You're then going to use TCDF. So remember, you use your lower t, your upper t, and then your df equals, and I'm sorry, this should say n sub d minus 1. Minus 1 got left off of there somehow. And then you're going to then be using your, if you use the calculator function, it's just t-test, but you do it using the difference list. Usually you have that in L3. So I usually do t-test on the difference list. If you move into the t-interval, it's to estimate the mean difference. So now, instead of testing a hypothesized difference, you're estimating that mean difference. Conditions are all the same, so it should be all good there. Your critical value is t star. You use inverse t, and again, df should be n minus 1, n sub d minus 1. Here is your interval formula. It follows that same format. We got our statistic plus or minus your critical value times that standard deviation or standard error. And then the calculator function is just t-interval using the difference list, so usually using L3. Okay, so if you wanted to copy that stuff down, feel free to pause the video and then come on back. All right, okay, next up is the question of the day. So I'll read it to you, and then I'll give you a few minutes to pause and select your best answer. This is just a multiple choice question, but this one should get submitted to Schoology, and then in Schoology, write down a reason why you picked that answer. All right, so it reads, the manager of a factory wants to compare the mean number of units assembled per employee in a week for 2 assembly techniques. 200 employees from the factory are randomly selected, and each is randomly assigned to one of the 2 techniques. After teaching 100 employees one technique and 100 employees the other technique, the manager records the number of units each of the employee assembles in 1 week. Which of the following would be the most appropriate inferential statistic test in this situation? And then you have to pick from 1 sample z-test, 2 sample t-test, paired t-test, or the 1 sample t-test. All right, take a second, pause the video, think through it, pick your best choice, submit that to Schoology, and then if you want to come on back and check the answer. Okay, so it does tell us right away in the beginning of the problem that we're looking for the mean number of units assembled. So we are doing a mean here. So what that really means is we can eliminate the z-test, right? So usually when we're doing a mean test, we're using the t-test, the t-distribution, so we can get rid of that z-test. We know that we have 200 employees, and they are randomly assigned one of the 2 techniques. So basically what we have is we're going to have a sample of 100 employees doing the first technique and 100 employees doing the second technique. So we know that we will have 2 samples, so that will allow us to eliminate D. So that basically takes us down to the 2 sample t-test or the paired t-test. So what this one is actually the 2 sample t-test. So that is B. And let me tell you why it's not paired. So it's not paired because you have 2 different sets of people doing 2 different types of things. If it were paired, what you would do is you would have just one group of employees doing both techniques and then comparing. But in this case, because you have 2 separate groups doing the 2 different techniques, it's just a 2 sample t-test. We would compare the mean number of units for each of those 2 groups, and then we would again do that 2 sample t-test for mu1 minus mu2. So the correct answer is B. Hopefully you got that one right. Okay, so let's move into our next topic here. Again, ChiSquare Tests. So that word is pronounced chi, and chi is a Greek letter, and I usually make my chi's like that. It's kind of like an X, but one side's a little curly. So chi-square is our new kind of statistic that we're going to learn. All right, so what I have here on this slide is z-tests for proportions are used for categorical or qualitative data. T-tests for means are used for numerical or quantitative data. So we've been talking about that quite a bit. So z-tests for proportions, t-tests for means. And then I have chi-square tests are also used for categorical data. And there's 3 types of chi-square tests that we're going to learn today. So I'm going to go through this first one called goodness of fit. These second 2 are actually very similar. There's a couple subtle differences, but actually the math is all the same. So the test for homogeneity and the test for independence. So for the goodness of fit test, I know it's kind of a strange term, goodness of fit. But what we do that when we have one population, we're studying one variable that has multiple categories. So that is the goodness of fit test. The test for homogeneity is when you have 2 or more populations, one variable with multiple categories. And the test for independence is one population, so now we're back to one population, and we have 2 variables where each of those variables have multiple categories. And again, this is all for categorical or qualitative data. So we're measuring kind of, different a variable with categories rather than with numbers. Okay, so we're going to start with the goodness of fit test, and then we'll get to the other 2 tests. And here is the context. The Trix rabbit just can't resist those fruity flavors. Raspberry red, lemony lemon, orangey orange, grapey purple, and watermelon. All right, so those are the different flavors in a Trix box. This is from generalmills.com. All right, a curious statistics student sorted an entire box of Trix and found the following distribution for the pieces of cereal. So there were 530 raspberry red pieces, 470 lemony lemon, 420 orangey orange, 610 grapey purple, and 585 watermelon. All right, so those are the observed frequencies. So that's how many times this student observed these categories occurring. All right, so then, do the 5 Trix flavors seem to be evenly distributed? All right, so if we look at that question, do they seem to be evenly distributed? And I'd probably say no. You can see that orangey orange happened 420 times. Grapey purple was 610. We can already see there's a pretty big difference there. And then it goes 470, 530, 585. So it doesn't seem like they're perfect. They're not super far off, but it doesn't seem like they are, too evenly distributed, I guess. All right, now let's think about if the flavors were evenly distributed, how many of each would we expect? So let's add an expected column to the previous table. All right, so what we would want to think about is, okay, if we had all of these categories evenly distributed, basically we would want the same number in each of these frequency spots here. So the way we can figure out how many would fall in each of those categories is basically if we just take the sum, right? We've been calling that n, and divide it by the number of categories, in this case 5, we could figure out what would be the expected frequencies if they were evenly distributed. All right, so I'm going to go to my calculator here and type these into a list. So I have those in there already in L1, and I'm going to do the sum of L1. I could have just added these up easily as well, but I'm going to just use my calculator. So to get to sum, you go to, second stat to the list menu. You go over to math and down to sum, number 5, and I want to sum L1. So I get 2,615 total number of pieces. Now, if I divide that evenly among the 5 categories, I end up with 523. So this would be 523. And what I can do then is make another table here with my expected frequencies. So notice that I have 523. All right, so now if we look at this, we can see that like raspberry red actually was pretty close to what we would expect if we if the flavor categories were evenly distributed. But we can definitely see that orangey orange is pretty far away. That's over 100 pieces off. Grapey purple, it seems like it's a little bit higher than you would think. Lemon and watermelon are a little bit closer, but still a little bit off. Okay, so what we're going to do is we're going to calculate a new statistic. So this new statistic is called chi-square, and it measures how close the observed frequencies are to the expected frequencies. And again, we abbreviate it chi-square. So usually, again, I draw it like that. So that is chi-square. And basically what it does is it measures O minus E squared, where O is observed and E is expected. So basically what you're going to do is you're going to take the difference between O and E, and so you're going to subtract. Then what you're going to do is you're going to square those numbers, and we do that to keep them positive. We don't want those differences all to cancel out when we add them up, so we need to square them to make them positive, make the difference positive. We're then going to divide by E as a way to kind of make it a little bit more relative to what we expected. And then what we're going to do at the end is we are going to take the sum. So we're going to add up all of those contributing values. So what I'm going to do is I'm going to go to my list, and in L2, I'm going to type in 523 for each. Oops. All right, let's try that again. So 523 for each of these. All right, and then what I'm going to do is in L3, I'm going to go up and hit L3, and I'm basically going to type in that formula without the sum, and I'm going to be using L1 and L2 for O and E. So I'm just going to go L1 minus L2 squared divided by E, which is an L2. So then I go ahead and hit enter there, and that's going to give me, again, these contributing values, or the contributions is sometimes what it's called. So this is 0.09, this is 5.37, this is 20.29, 14.47, and 7.35. So I can see that the numbers, so the contributions that are small had observed and expected frequencies that were very close. The contributions that were large, like orangey orange, was over 20. That's because the observed values and expected values are pretty far apart. So then what I'm going to do is I want then to take the sum of those contributions. So I'm going to go into my home screen, and I'm going to hit second stat. I'm going to tab over to math, and now I'm going to do the sum of L3. And that gives me a chi-square value of 47.57. 47.57. So that is what chi-square is. That's my statistic here. All right, so that's how I would notate it. Okay, so but what does that mean, right? So we've calculated it, but what does it mean? So what we do know is that if the observed values are the same as the expected values, chi-square would equal 0, right? So if these two lists were the same, right, we would have a chi-square value of 0. If the observed values and the expected values are very different, then chi-square will be very large. So to determine how large is too large, we need to consider the sampling distribution of chi-square. And the sampling distribution is based on degrees of freedom. So just like the t-distribution, the degrees of freedom, or the distribution is based on the degrees of freedom. Now we have a different degrees of freedom formula. It doesn't actually involve the sample size this time. It involves the number of categories. So the degrees of freedom is just equal to k minus 1, where k is the number of categories. So in this case, I have 5 categories, so I would have 4 degrees of freedom. So that's what I would be using in mind. Okay, so now if you're in the slides, you can click on this link, and that will bring you to a little applet where I'm going to show you the chi-square distribution. So up in here, there's this kind of character. It looks like a V. That is the degrees of freedom. So the degree, depending on the degrees of freedom, you're going to have a different chi-square distribution, just like the t-distribution. So what I'm going to do is I'm going to show you. So this is the chi distribution that we're going to use for 4 degrees of freedom. We can see that it has a positive skew, so it's skewed to the right. Right. We can see some of these chi-square values along the bottom here. So we can see that it starts at 0. It starts to trail off. Definitely when you're getting around 14, it starts to get really close to that axis. Let's look at what it looks like if we bump up the degrees of freedom. Let's do like 20 degrees of freedom. Right, we can still see it is slightly skewed to the right. It's definitely has a higher center, so it's centered at a larger value. So we would expect a higher chi-square value with more categories, and also more spread out. Okay, and if I jump down to and change this to like 2 degrees of freedom. There we go. Okay, now we can see it's really skewed to the right. Much smaller expected chi-square values. So if we go back to our question here, so for the tricks example, we had 4 degrees of freedom, and so the distribution is gonna look like this. And remember that we had a chi-square value of 47.57. Well, I can see right away that number is going to be that's going to give me, or it's going to be really unlikely. And I can actually type this in here, and we can do this on the calculator. I'll show you in a minute. But what I can do there is if I type in that number here for x, 47.57, and I'm doing a greater than, and notice that it gives me a probability, so a right-tailed probability of 0, right? It's going to be extremely unlikely. Whereas let's say I had a chi-square value of 10. Sorry. So now I can see that probability to the right of 10 is about 4%. So this would be the distribution that we're using when we're calculating a p-value. So let's just quickly summarize that sampling distribution. So the sampling distribution of chi-square has a positive skew, or sometimes we call it a right skew, right, skewed to the right. As k increases, the variability of the distribution increases. So we could see it was becoming more spread out as k got bigger. As k increases, the center of the chi-square distribution increases. You would expect larger chi-square values. So now, how likely did our chi-square value seem to be? We saw that it was basically 0. So it's very, very unlikely. And how have we determined likelihood in the past? A p-value. So we can actually, on our calculator, use this function called chi-square CDF. And what we do for chi-square CDF, we have 3 arguments. The first argument is your chi-square value. We always do an upper-tailed test on using chi-square CDF, so I always just use that 1E99 for my upper bound. And then your third argument is degrees of freedom, where k is the number of categories. And once you have that p-value, you can compare it to alpha. So I'm going to show you the calculator now. Okay, so what we do, we can go to second vars. And if we go down here to chi-square CDF, make sure you use the CDF function when you're calculating a p-value. Your lower value was that 47.57. Your upper is 1E99. That's 10 to the 99th, a really large number. Degrees of freedom was 4. And then we'll hit paste, enter. And we get a p-value of 1.16 times 10 to the negative 9th, right? Which is going to be a very small p-value. So 1.16 times 10 to the negative 9th. While I have the calculator up, I'm also going to show you the calculator trick. So if you hit stat and then over to tests and scroll down, there is a chi-square GOF test. Chi-square GOF test. Hit enter on that. And then if you put this, your observed is L1, expected is L2. That's usually just going to stay the same. That's where you're going to put those numbers in your list. We do need to modify the degrees of freedom, so we have 4 degrees of freedom. And then if I hit calculate, notice that it gave me that chi-square value right off the bat and a p-value. So you actually don't really have to make that L3 list where you type in the formula, because you can use chi-square GOF test to actually get your chi-square value. And then you can use this also to get the p-value. Okay, so now let's go through the 4 steps here on kind of how to put this in. So step 1, you're going to name your procedure, you're going to define the parameters of interest, and you're going to write hypotheses. So I will conduct a chi-square goodness of fit test. Now how I'm defining my parameters here, so I'm going to be, since I have categorical variable, I'm going to be using proportion. So in this case, I have 5 flavor categories, so I'm going to have 5 proportions. So I said the parameters of interest, P1, comma P2, dot, 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 comma P5, denote the true proportion of trick cereal pieces that fall into the 5 flavor categories. So that's just kind of a broad statement that defines all of my parameters. Now, my null hypothesis is I need to hypothesize what those proportions are going to be. Well, I know in this case that they're going to be evenly distributed. I'm trying to show, are they evenly distributed? So each of these, I'm going to hypothesize that they are evenly distributed. So all 5 of those proportions are going to equal 0.2. So P1 equals 0.2, P2 equals 0.2, etc. So that doesn't always have to be the case. Sometimes they might be, you might be comparing your observed value to maybe expected values that are not evenly distributed but fall into some other distribution. So maybe that P1 is half of the group, and then P2 and P3 are both a quarter, so 0.25. So there will be cases when these numbers aren't all the same. So yeah. So then our alternate, I usually just write that the null is not true. So it doesn't mean that they're all, like my alternate, it doesn't mean that they're all not equal to 0.2. It just means that, so don't write that as an alternative, that they're all not equal. Because you could just have one proportion that's different. That's going to throw off at least one more proportion. But it could be that some of these proportions are 0.2. But we're just trying to show that they're not all 0.2. So that's what you do in step 1. Step 2, you're going to verify your conditions. So your conditions here are pretty similar to what we've had. So observed values came from a random sample or a randomized experiment. Sample size is less than 10% of the population if you were sampling without replacement. And then this is the new one. All expected counts are greater than or equal to 5. So we kind of have a new magic number of 5, and that is the expected counts. So this box so then to apply those conditions to our tricks example, this box is a random sample of trick cereal and less than 10% of all trick cereal pieces. All expected frequencies are greater than 5, so your conditions are met here. All right, so that's step 2. Step 3, we carry out the procedure. So we basically find a p-value using either chi-square CDF or chi-square GOF test. So I showed you that. And again, we did get a really small p-value. All right, step 4 then, you interpret in context. So you need a decision comparing your p-value to alpha, and then we do write the conclusion in context. Since the p-value is very small, we do reject the null. So just like we've done in the past. So then we say there is significant evidence to conclude that at least one of the flavor proportions differs from the corresponding proportion for all flavors, right? So we know that we do not have an evenly distributed function here. Okay, so that is your 4-step process. So if you need to, pause the video, take a minute to digest that, and then we're going to move on to our next 2 chi-square tests. All right, so the next 2 tests are the chi-square test for homogeneity and the chi-square test for independence. So underneath them so remember with the goodness of fit test, we had one population and one variable. So our population in the first one was trick cereal pieces, and we had one variable, and the variable was the flavor, and we ended up having 5 categories for that. So with homogeneity is you're going to do something similar, but what you're going to be doing is you're comparing 2 populations against that one variable. So maybe you are you're looking at the distribution of students in each grade from year to year, right? So maybe you'd look at 2021 distribution of grades at a school, and then compare that to 2018 to see if there is a significant change in the proportion of students in each grade level. So that would be considered a test for homogeneity because you have 2 very distinct populations. You have a population from 2011 and a population from 2018. Whereas a test for independence is you're going to have one population against 2 variables. So now you're measuring 2 different things for that same population. So like a common example would be if you were to take a sample of a big group of people and compare their political affiliation to their maybe income bracket. So, which, if you had them making 0 to 50,000 per year or 50,000 to 100,000 per year, right? So if you were to break those up into income categories, that would be considered a time when you could do a chi-square test for independence. All right, so in both of these conditions, you have to name the procedure and write hypotheses. Right, so here is your procedure, either a chi-square test for homogeneity or a chi-square test for independence. So again, with homogeneity, you're basically trying to show that your 2 populations either are or aren't homogeneous, which means that they're similar. In the chi-square test for independence, you're testing whether 2 variables are independent. We've talked a little bit about independence back in our probability unit. Okay, so your null hypothesis for a chi-square test for homogeneity is there is no difference in the categorical variable, so I have that in brackets because you would put in your own variable there, across populations or treatments. You can also use this in a randomized experiment, so you may have then some treatments instead of different populations. And then if that's your null, then your alternate then is there is a difference in the categorical variable across populations or treatments. So you'll notice that in homogeneity, you don't need any numbers in your null and alternative. You're just writing a statement in words. And then same thing for test for independence, no numbers here. Your null is that you basically just write your 2 variables. So variable 1 and variable 2 are independent for a given population, and then you write down what your population is. And then your alternative, categorical variable 1 and categorical variable number 2 are not independent in a given population. So that's what you would be writing in that case. Okay, step 2, conditions. They're pretty similar. Observed values came from a stratified random sample or a randomized experiment, right? So in a test for homogeneity, you generally have 2 samples, right? So you have 2 samples from those 2 populations, or it's possible that you even have more samples. So I should say 2 or more. All right. Sample size is less than 10% of the population size, so that needs to be true for each of the samples. And again, just like we had with the homogeneity, all expected counts are greater than or equal to 5. Test for independence. Now, since you only have 1 population, you just need a 1 sample, so you do need a simple random sample. And then sample sizes are less than 10% of their population size, or the sample size is less than 10% of the population size. And again, we see that same condition again, all expected counts are greater than or equal to 5. So that's really the only new condition when you're doing chi-square tests. All right, step 4. Okay, this is where it's a little bit different. So you have, it's different than the goodness of fit test, but the math in step 3 is exactly the same for both homogeneity and independence. So there's a couple things that you have to do. You have to calculate your expected counts. So this is a formula that we use, and I'll show you how to use this in a minute. You're going to calculate chi-square, right? So that's that same chi-square formula that we had for goodness of fit. The degrees of freedom formula is a little bit different. So because you're doing, for homogeneity, multiple populations for a variable with multiple categories, instead of just having 2 lists of data like we did in goodness of fit test, we're going to have a matrix, and I'll show you that in a minute. And same thing with independence. You're going to have 1 population, but you have 2 variables with multiple categories, so you're going to have a matrix. So to calculate degrees of freedom, you do rows minus 1 times columns minus 1. So you take how many rows you have, subtract 1, how many columns you have, subtract 1, multiply those 2 numbers together. That gives you your degrees of freedom. And then you calculate a p-value using either chi-square CDF or chi-square test. And again, I'll show you both of those in a minute. So once you have all that stuff, you get to step 4, right? You have the same, compare your p-value to alpha, write your conclusion, right? So you're either going to reject the null or fail to reject the null. So your statement then is either there is or isn't significant evidence of a difference in the categorical variable across populations or treatments, or there is, so that's for homogeneity. Then for independence, you'd say there is or there is not significant evidence that categorical variable 1 and categorical variable 2 are not independent. Okay, so that is step 4. So again, just compare p-value to alpha and then interpret. Okay, so I'm just going to run through an example here. I'll show you kind of the math first, and then I have kind of the answers in the 4 steps below here. So a random sample of 334 adult males were asked to categorize their smoking level and exercise level. The results are below. Test whether there is an association between exercise level and smoking level at the 0.05 level. Okay, so that's our alpha value right there. It does say a random sample of 334 adult males. So in this case, we just have 1 sample. That's a clue right away that we're going to be doing a test for independence and not a test for homogeneity. Then the 2 variables, smoking level and exercise level. So they have these as categories. So this is these are 2 qualitative or 2 categorical variables. So smoking level was heavy, never, occasionally, or regularly. Exercise level, frequently, none, or some. Okay, so what we're going to do first I'm going to add a little grand total. We know that all of these numbers together would be, 334. So that is my n value. Okay, so if we look at the conditions that we need all of our expected counts greater than or equal to 5. And we calculate expected counts using row total times column total over grand total. So let's just calculate a couple of these expected counts. I'm not going to do all of them by hand, but we will do a couple. So let's do this first expected count. Our expected counts we usually put in parentheses next to our observed counts in the table. So what we have to do is we have to take our grand total, our row total. So the row total for heavy, so if I add those up, 12 plus 10 plus 5, that is 27. I do the column total, so what would that be? 120, 132, 133. And then I'm going to take, and in my calculator, I'm going to do row total times total divided by grand total. So row total 27 times column total 133. And then I'm going to divide by the grand total of 334. So this expected count is 10.8. Excuse me. Okay, so then I could continue to do those. So I could do, if I wanted to do the next one. So for none, right, I would use the same row total. I would calculate this column total and divide it by 334. So it does get a little arduous, especially if you have so many values. So you can do this on the calculator, and I'm going to show you that next. So we're going to be using the matrix function, and to access that, you go to second, and then you can see in blue it says matrix above like the little inverse key. So we're going to hit that button there. Okay, and this will allow us to type in data into a matrix, but I'm going to have to go over and hit edit first, and I'm going to hit edit on matrix A. What it's going to ask you first are the dimensions of the matrix. It's always rows by column. So I have 4 rows and I have 3 columns. And then I'm just going to type those in. And you can do this along with me. Feel free to pause if you need to. So again, I'm just typing each of these observed counts in. And all right, like so. So again, pause the video if you need to. And then I'm going to go to, I'm going to go back to my home screen, and I'm going to go and I'm going to use the ChiSquare Tests. So I hit Stat, I tabbed over to Tests, and I'm going to go down to where it says ChiSquare Test. Okay, so what I have here, I'm going to have my observed values in matrix A. I have that already. What this will do is it'll put my expected values into matrix B, and then I'm going to hit calculate. And notice it'll give me my chi-square value and my p-value. So I'm actually going to use those numbers in a minute, but I'll come back to that. Let me just show you where now your observed values are. Oops. So if you go to second matrix again, now you'll notice there's a matrix B. So I'm going to go over and edit matrix B, and I can see that I have these observed counts. Maybe I made a mistake in my addition here. I think... Sorry, this number here, my bad, should have been 143. I think that's right. Or no, 144. Sorry, 143. So sorry about that. So the correct expected value there was 11.56. That's another reason why you should use your calculator, and then you won't make some simple addition mistakes. Okay, so that gives you all of those expected counts. We could write them all down there if we wanted to in parentheses next to the numbers. It would kind of give us an idea of how each of those categories differs from what we would expect. But now let's just go through and run through the 4 steps now that we have a little bit of that background stuff. So this is a test for independence, so I wrote that first. My hypotheses, smoking level and exercise level, are independent. Smoking and exercise level are dependent. Notice like if you're doing this on the AP exam, you would just go ahead and write the expected counts next to your observed counts. So that's step 1. Step 2, I did have 1 random sample. All of those expected counts are greater than 5, and I can look through those. My smallest expected count looks like 9.6, but 6.5. That's still bigger than 5. So basically, if you just look for the smallest number, compare that to 5, you're good. Sample size is less than 10% of the adult male population. That's another check. So the conditions are met. My chi-square value, 17.984. And again, if I look at what I had when I did chi-square test, stat test, chi-square test. Right, I can see that, again, that chi-square value, 17.984, that's the one I got there. P-value, 0.0063. And also do write down your degrees of freedom. We had 6 degrees of freedom. 4 minus 1 times 3 minus 1 would be 3 times 2, which is 6. All right, so we have a small p-value. It's less than alpha, so we can reject the null. So there is significant evidence to conclude that there is an association between smoking and exercise level. I wrote it like that. Another way to write your conclusion would be there is significant evidence to conclude that that smoking and exercise levels are not independent for adult males. All right, so that gives you the quick example of the chi-square test for independence. Homogeneity, step 3 is exactly the same for homogeneity. Some of the wording will be a little bit different, but you just kind of follow that format that I had presented earlier. Okay, so those are your chi-square tests. We do have textbook homework. So these go through, there's one 4-step problem of each type. So you'll have a chance to practice that. So that's what you should be working on for the day 1 assignment. And then there's a bunch of AP classroom videos in Unit 8. I kind of went through them pretty quickly, so if you want to get a little bit more help with any of these 3 tests, feel free to jump on those AP classroom videos. Okay, that's it for today. I hope you all have a great day, and we'll see you next time. Thanks for watching.